Hello everyone. Welcome back to Debugging with K-Tips. So far, we've laid the groundwork, what machine learning is, how it differs from traditional programming, and the major types of learning, supervised, unsupervised, and reinforcement learning. If you haven't watched those videos yet, check the link appearing now. I'll also add them in the description, so feel free to watch them. And don't forget to like and share, as it supports this volunteer work. Now it's time to get our hands dirty by building our very first supervised learning model from scratch using Python in a Jupyter Notebook. Our goal is to teach a machine to learn the relationship between an input and an output using labeled data. This is classic supervised learning. You may want to visit the link appearing now to review the different types of machine learning. Let's start with a very simple and clear dataset. The input x is an array from 1 to 10. And the output is just the square of the input. So, for example, when the input is 1, the output will be 1 squared, which is 1. When the input is 2, the output will be 2 squared, which is 4, and so on. As you can see, the pattern is straightforward. This makes it really easy to check whether our model is learning the right thing. We're going to build a polynomial model, meaning that instead of just a line, it can learn curves defined by y predicted equals w1 times x plus w2 times x squared plus bias. That gives us enough flexibility to capture the actual relationship. Don't worry, we're still keeping things simple and interpretable. Before we code, let's walk through the math briefly. We want to train a model to minimize the difference between its predictions and the true values. The most common way to measure that difference is mean squared error, MSE. The loss is the average of the squared differences between predicted values and true values. We'll use gradient descent to adjust our weights W1, W2, and bias until the loss is as small as possible. To do that, we'll initialize the weights randomly. For each epoch, one pass through the data. Calculate predictions. Compute the loss. Calculate gradients. Update weights using the gradients and the learning rate. But wait, what do we actually mean by learning rate? When you start programming machine learning models, you'll come across something called hyperparameters. These are settings that control how the model learns. There are quite a few of them, but in this video, we're going to focus on 3 key ones: the learning rate, the number of epochs, and the training loop, the core of how learning actually happens. The learning rate is a small number that determines how big a step the model takes when adjusting the weight and bias. If the step is too small, learning will be slow, and it might get stuck before reaching the best solution. If the step is too large, learning can overshoot the solution and fail to converge. So we want a learning rate that's just right. For this example, we'll start with something like learning rate equals 0.0001. So, the learning rate controls how big each step is as the model updates its weights, but there's also the question of how many steps we should take. That's where epochs come in. An epoch is one full pass through the training data. And typically, we train a model over many epochs, gradually improving its accuracy with each pass. If we train for only a few epochs, the model won't have enough time to learn. If we train for too many, it might overfit or waste resources. So we need to choose a reasonable number, say 100 epochs, to give the model time to learn without going overboard. Now we're ready to put everything together into a training loop. Here's what happens inside. Loop through the training data for a number of epochs. For each data point, calculate the prediction. Compute the loss, how wrong the prediction was. Calculate the gradients, how much to adjust weight and bias. Update weight and bias in the direction that reduces the loss. Optionally print the loss every few epochs to see progress. This is the core of gradient descent in action. In the next video, we'll apply this same idea to real-world data with multiple features, like predicting house prices using square footage, location, and more, and we'll use tools like TensorFlow and Keras to handle the math for us. We'll even build an LSTM for time-based data later in the playlist. So be sure to subscribe and turn on notifications to follow along as we go from toy problems to real models. Now it's time to bring our model to life with code. I'm working inside a development container using Visual Studio Code, and everything is running in a Jupyter Notebook. This setup makes it super easy to test code and visualize results in real time. If you're not familiar with dev containers or how to set this up, don't worry, I've created dedicated videos that walk you through the entire process. Just click the link that's appearing now, and you'll be ready to follow along with this code. So, here we're implementing our supervised learning model from scratch. The model is designed to learn the relationship y predicted equals w1 times x plus w2 times x squared plus bias. This is a simple polynomial regression problem trained using gradient descent. We'll use Plotly graph objects to visualize the data and our model's predictions. Since Plotly isn't installed in this development container yet, we'll begin by installing it. Then, we'll import Plotly along with NumPy for our numerical operations. Let's go ahead and run the first cell. Next, we define our data. In this case, the input data x is simply a sequence of numbers from 1 to 10, and the output y is the square of each corresponding value in x. This means that y follows the relationship y equals x squared. We use the numpy.array function to define these arrays efficiently and make sure they're vectorized for numerical operations later on. Let's run this cell. Now let's talk about the model. We're going to use a simple polynomial regression model, which allows us to capture curved relationships by introducing a second-degree term. To start training, we need to initialize the model parameters. W1 is the weight for the linear term x. W2 is the weight for the quadratic term x squared. Bias is just a constant shift applied to the output. We initialize all of these using numpy.random.ran, which generates random values from a standard normal distribution. This randomness helps avoid symmetry in training and ensures the model starts with some variability. Let's run this cell. Next, we define two important hyperparameters. Learning rate, this controls how big a step the model takes when updating weights during training. We're using a small value here, 0.0001, to ensure learning is stable and gradual. Epochs, this tells us how many times the model should loop over the entire dataset during training. We'll train for 100 epochs. Let's execute this. Now that the data and parameters are ready, we define our model as a Python function named model. It takes an input x and returns the predicted output using the equation we just discussed. We go ahead and run the cell. Next, we need a way to measure how well the model is performing. In our case, we're using mean squared error, MSE, one of the most commonly used loss functions for regression tasks. MSE works by computing the difference between the predicted values and the actual target values, squaring those differences, and then taking the average across all examples. In other words, if n is the number of data points, we calculate the squared difference for each point and then average them. In code, we implement this using numpy.mean function and basic vector operations. The lower this loss becomes, the better our model is doing at predicting the correct outputs. Let's go ahead and run this cell to initialize everything before we move on to training. Now that we've defined our model and the loss function, let's talk about how the model actually learns, and that brings us to gradients. To improve the model's predictions, we want to minimize the loss, in our case, the mean squared error. The way we do that is by calculating the gradient of the loss with respect to each parameter, the weights and the bias. This tells us how much the loss would change if we adjusted one of those parameters just a little bit. Let's first define the prediction error for a single data point. That's simply the predicted value minus the actual value. So, for a data point I, the error is the predicted y for that point, minus the true y value. This error is what we want to reduce. Let's start with the weight for the linear term x, which is w1. The gradient is calculated as 2 divided by the number of observations, which in our case is 10, multiplied by the sum of the error for each data point, times its corresponding x value. This tells us how sensitive the loss is to changes in W1, and in which direction we should update it. Next is the weight for the squared term, x squared, which is W2. Here, we compute 2 divided by the number of data points, multiplied by the sum of the error for each point times the square of its x value. This tells us how to adjust the coefficient for the curved part of our model. Finally, we have the bias. The gradient for the bias is 2 divided by the number of observations, multiplied by the sum of the errors across all data points. This helps shift the entire curve up or down to better fit the data. Once we have these gradients, we update each parameter, W1, W2, and the bias, by moving them a little bit in the opposite direction of the gradient. The size of this step is controlled by the learning rate. This process is called gradient descent, and it's how the model learns from the data step by step, gradually improving its predictions. We iterate through the training process for a set number of epochs, 100 in our case. For each epoch, 1. We make predictions using the current weights and bias. 2. We calculate the loss by comparing the predictions to the actual values. 3. We compute the gradients, the partial derivatives of the loss function with respect to the weights and bias. 4. We update the weights and bias using the gradients. In this loop, dLdW1, dLdW2, and dLdBias are the gradients, which tell us how much each parameter affects the loss. We update the parameters by subtracting the product of the learning rate and the corresponding gradient. This helps the model improve over time. Let's go ahead and run this. As you can see from the output, the loss is steadily decreasing over time, from about 0.6051 at the start to 0.5512 by epoch 91. This consistent drop indicates that the model is improving its predictions and gradually learning the pattern in the data. It's slowly adjusting the weights and bias to better fit the data. After training the model, we'll visualize the results using Plotly. Plotly allows us to create interactive plots, so we can easily inspect the model's predictions. First, we create an empty figure. Next, we add the true values, the squares of x, as blue markers on the plot. Then, we add the predicted values as a red line. Now that the model is trained, let's test it on a new, unseen value, x_new equals 11. It is important for the test input to have the same type as the train input. So in our case a 1-dim array. We can add this prediction to the plot as a green marker. Finally, we customize the layout of the plot, titles, axis labels, etc., and then display the plot. Lastly, we print the prediction for the new unseen input value to the console. In this code, we started by defining a simple polynomial relationship, y equals x squared, between input x and output y. We trained a model using gradient descent to approximate this relationship. We visualized the results using Plotly and tested the model on an unseen value. Now you can see how well the model performs by observing how closely the red line matches the blue dots in the plot. The green marker shows the model's prediction for a new value, x equals 11, and you can compare it to the actual value, y equals 121, which is 11 squared. The model's prediction for 11 squared is 119.74. This is pretty close to the true value. I love it. Do you love it too? Then like this video. If it was helpful for you, then share it with your friends and family. And that's our first supervised learning model. It's basic, but this foundation is what powers more advanced models like LSTMs. In the next video, we'll start scaling up. We'll explore how to handle multiple features, introduce more realistic data, and then move toward using powerful tools like NumPy, Pandas, TensorFlow, and Keras. If this helped you connect the theory to practice, go ahead and subscribe, and turn on notifications so you don't miss what's next. Happy coding and debugging with K-Tips. See you in the next one.